Good morning, I'm Cody Hendrickson. Today we're going to be talking about the data structure trees and some of the basic things that we can go along with them. This is for our CS2420 series, Data Structures and Algorithms. So there are many different types of trees. In fact, this is a tree. Wait, well, it's a dog in a tree, and although it's cute and photoshopped and it's not quite real, it's still kind of trees. So let's take a look at some of the trees that we can see here in our data structures class. We have lying trees, aka those trees we see outside. Now these trees are lying because of the fact that they have a multiple root system. Too many roots! As well as the fact they're pointing in the wrong direction. The roots are at the top, the leaves are at the bottom. What's going on? We have abstract trees. The abstract tree is just the idea of a concept of a tree, aka some way of holding data representation in a hierarchical fashion. One of the easiest ways to show that is with a diagram such as this. Hey, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No 12, but 13 and 14 because we took 12 out. Hey, abstract. Great. We have a binary search tree. This is something we'll be using all the time. In fact, it's probably the most common way of actually looking at a tree in a data structure perspective. And we have a data structure tree right here with a binary tree with some nodes. We have a binary tree node with a type data, what's going in right there, with the associated root, left, and right child pointers. Hey, we'll talk about that some more in just a bit. We also have a heap tree. This is the kind of tree that we actually use in our operating systems, so we can, or in our big scale of our data structures approach, we're going to actually retrieve the next available piece of memory for our system to use because we want to usually find the biggest available chunk that we can actually use inside our project. Weird, we want the data to do something. Cool. We have a wrong tree. What? Wrong tree? Oh, that. Yes, the cat is a wrong tree. It's not really a tree at all. It's a kitty. I'm so confused. What's going on? We have an AVL tree. AVL tree, fantastical approach of using a self-balancing binary tree. And we can see it right here with this cute little animation. We have a left-right case, a right-left case, a left-left case, right-right case, and then it'll become balanced. Yes! And we'll talk about that some more later on too. Taxonomical tree. Oh, wait. So we have mammals, and mammals there's kitties, and doggos. And there's floofers, woofers. Oh, yes. I love taxonomical trees that are fantastic. Deku tree. Oh, yeah, that's a tree. Not a data structure, but still a tree. Yeah. We have Happy Tree. Now, Happy Tree, oh, of course, Bob Ross has to be involved. How can we talk about trees and not talk about Bob Ross? We really should be having actually Bob Ross trees on everything we're talking about. We're talking about data structures at all, because Bob Ross makes everything happier and better. Yeah. Red-black trees are another type of self-balancing binary tree we'll take a look at here. And you can see right here that the red-black tree has a difference of between the nodes themselves, whether they're using a single bit of information to talk about whether it should be red or black, and all the leaves of the tree itself are black. And we'll talk more about that later. Logic tree. Logic. Well, you can make logical decisions inside a tree, especially when you're looking for advanced programs such as AI or actually planning out what's going to happen. But then we have this. Dog barks. Tree has bark, therefore dog is tree. Not quite logic, but hey, we'll say it's a tree. A 2, 3, 4 tree is another type of a multivariate tree where it's not simply just binary, and where it has either 2, 3, or 4 nodes. And we'll take a look at that another time. An N-ary tree is even more complex, where I can have any number of nodes. The N meaning the mathematical concept of any round number, and binary tree being the concept where N is 2. We also have the inheritance tree, which we see inside Java or C++, like we're looking at right now. We're talking about where they have the idea of a relationship of data structures and how they relate to each other in a hierarchical fashion, aka inheritance. You also might see this in this little thing, with your family, talking about who your grandparents were and their grandparents. Oh, yeah. And then there's a B tree. It's a special type of tree, really cool stuff. And bamboozled again. Oh my gosh, that's a puggo. Not a tree. But hey, this and many other trees can be talked about inside data structures class. Thanks again for lucidchart for providing a great little structure for how we can actually address these concepts. But let's go ahead and move on. So when we're talking about trees, it's the idea of a hierarchical data structure, aka there's a way we're looking at data in some hierarchy, aka this is above this, which is next to this, and there's some relationship between these different subchildren and the one that's above it. And so we have that idea that we're going to have a hierarchy of our data structure, and we can use that organization to do something. Now, you can actually have a tree where the hierarchy means nothing. Why? No, we're not going to use that. We're actually going to use trees that actually can store stuff. Now, a tree itself can be just simply a simple node and just all the connections that go from that. But with the idea of having some structural approach where we want to have some private information versus public access, we're not going to be doing that, and so we have our tree composed of nodes. And so the node itself is what has the data and makes the connections between it, but then the actual structural approach is done by the tree, and we'll use that. And this is like the idea of a CRUD operation, if you may be talking about a database, you might have seen those before. But the idea that the tree itself is responsible for the creation, the removal, the update, the displaying of information, but the node itself just holds little tiny pieces of data. Again, it's a distribution of roles. Who has what job? And so the tree has the job of doing all the work. The node itself has its own little tiny job. It makes life a lot easier. Now, a tree is not sequential. In fact, it's not even linear at all. And so because of the fact it's neither sequential nor linear, we're not going to be using indices to talk about where we are in the tree. Because the relationship of the tree is the way the data itself relates to itself. That's that hierarchy again that we were just talking about a minute ago. And so we don't have an index like, oh, I want to go to the 5th spot in the tree. No, instead, I have paths to values. And we'll talk about that another time. Now, we have an abstract base class for a tree. Now, when we're working with C++, the abstract base class is just like, oh, everything equals 0 because we don't do any definition for it. This would be an abstract class in Java, then same thing in Swift. We're going to have no implementation for it. It's just that here's the framework that we're going to automatically have. For Swift to actually be a protocol. But hey, we're good. Now, in our tree of type, when we're talking about this, we have our basic methods we have to have. We have them grouped into 3 special groups. We have our informational methods, which are the things we're actually looking at to tell us about the tree, aka how big it is, how wide it is, whether or not it makes sense going on left or right sides for comparison. Then we have the ways of traversing the tree, and there are 3 major traversals, which we'll talk about in another video. Take a look at that another time if you have the chance. And then we have the actual work methods of the tree, aka I want to put something in, take something out, or see if it's something that's inside the tree. And those are the operational methods. And so that's how we actually organize the tree. Now these are the basic methods that all trees, regardless of implementation that we saw in that other thing, well, except for the cute little Pogo tree. This is the methods that all trees are going to have. The way they function within that, of course, we handle by the individual trees themselves. And again, this is why we have the tree quality happen in the tree class and not inside the node, because we want to have that division of resources appropriately maintained. Now, we'll talk about our binary tree node as our first example we're going to be using for this, because a binary tree node, so again, that's that main way we actually handle trees inside the data structures class, and what we're looking about when we're actually talking about how we're going to organize trees in a hierarchical fashion. And so we have our inheritance structure right here where we have the inheritance tree. Oh wait, that's what we just talked about too. We have a node of type, which has a data member called data, and that has the constructors and the get data and set data accessor methods that we use to access that. And then the subclass of that, the binary tree node of type, has the associated additional data members of root, left child, and right child. And again, we have these as private because we want to have the idea that only the owner of that individual object can affect those things, and we can use the accessor methods as appropriate inside that. And so we have our getters and setters for the left root and right child pointers. And then when we're building our tree node, we only have a data parameter because we don't want to actually cause some confusion, because again, when we're creating a constructor, that signature itself, we are only allowed so many different things, and I don't want to have a whole bunch of nulls inside my parameters when I'm creating something, because too many nulls, kind of messy, not sure which one I'm going to pass to which the right value, and we don't need to provide extra information when we're creating a value, so it's a lot easier simply to have associated methods to update the correct values as needed, which I think actually, although it requires a couple of method calls, makes the actual structure and definition of that class a lot easier to work with, and so that's why we're using this right here. Then we take a look at their binary search tree. So many methods. I know, there's a lot of stuff here. But we take a look at this right here. We can see that we have inside our binary search tree, we have a data member now. In our previous one, we didn't have a data member. We have a data member here for our binary search tree because we want to make this that one be more abstract. This one's more specific. And our data member right here is a root data member. It's the node that we're talking to at the root of the tree. We want to keep track of that. It's kind of important. And then we have a bunch of methods. So we have our constructor and our get root and set root, just in case, for some bizarre reason, we might want to actually change that outside of the class. Probably don't want to do it, but just in case, we have availability for that. We then have our recursive helper methods, and this is where all of the work is going to happen inside our project. Because when we're talking about the tree, we have our abstract class methods that belong to all trees right there, and those are like, oh, this is going to call the appropriate thing for the right stuff, because again, they have no parameters. But then we go into the actual work where it happens, and that's going to happen inside these helper methods. Because again, although we could create a tree using a non-recursive structure, go take a look on Google. It's your friend, right? But take a look on Google. Look at doing a non-recursive tree. You have to have so many extra data structures on top of data structures on top of data structures. It's going to make more work for you, plus you have a lot more code to write. And it doesn't actually help with the understanding, nor the implementation, nor the efficiency. So more work, more code, less efficient, harder to explain. Yeah, no, we're not going to take that route. We're going to go here and use recursion. It does require us to actually practice with the stuff and actually look at what's happening, but it's a better time overall. Now, when we're talking about the binary tree, we have the idea that we're going to go left or right based on the relationship of the data, and if it's equal, we don't go anywhere. Now, when we're talking binary search trees, we want to make sure that we keep in mind that we're always only going to be using unsorted, aka random data. If you're pushing in a whole bunch of sorted data, your tree, instead of being this cool little triangle thing shaped of stuff, you get a line. With extra work, less efficiency. Oh, wait, we just talked about that. Not something we actually want to go for. So we want to use recursion as our main approach for this, and we want to use the idea of using this for unsorted data. That's where this becomes a lot of things. Now, there's a lot of code and a lot of algorithms that go into this. And so take a look at the actual structure that goes into this and how the details happen inside the binary search tree. That's something you definitely want to practice. But this is the one that we're using for the majority of what we're doing when we're talking about a tree and using the data structure. Now, new tree, who dis? Now, we have a picture right here of Panda, the largest organism in the world, right here in Utah. It's this huge mega structure of tree. It's all the same tree, everywhere, all over. But that's not actually how trees work in the data structures environment or in the side computer science as a whole, because not all the trees are the same. We have different types of trees, and so the new tree who dis meme is a great way to approach this. We have our self-balancing binary trees of the AVL and the red-black tree we just mentioned earlier, and they're the ones that their job is a binary tree, but they balance themselves as they go through, and they have a way to keep your organization and your structure really nice. Makes it for a more compact and efficient tree. In science, we have the taxonomy tree. We're going to actually talk about things in a relationship and build this up. You might have had that like biology class back in junior high, high school, when you're actually talking about how that relationship of stuff, you know, the phylum, kingdom, genus, oh wait, yeah, that. That's a hierarchical system that is a tree that we can actually use to do that. And so it's a great way to actually explain things inside science. And then we have some other important trees. The min or max heap, finding the biggest or the smallest piece available and keeping that at the root so we can easily grab it and then remove it as needed. Really cool stuff. Again, like we talked about, the 2, 3, 4 tree, where we can have the tree build to the appropriate size of 2, 3, or 4 subnodes underneath it, and it can build itself and have a much more enhanced capability, maybe for a good description of that. Inheritance trees, we talked about, we just saw an example of when we were talking about the relationship between node and binary tree node. We have a relationship of data structures inside our own projects. The Huffman coding tree is the one I want you to take a look at after you watch this video, because the Huffman coding tree is amazing. It's an easy way to express the concept of compression and make it so that you can explain this and work with it on a very basic level. It's a really cool example of how to actually use a tree to solve a problem and actually do some really cool stuff with that. So that's what I'd like you to take a look at after doing this. Then we have the B tree. B tree is really amazing. There's a whole bunch of stuff that can be attached to that. Again, using the magic of the internet and looking up what a B tree is, you can find some really cool stuff. We'll cover that another time in a lecture, but for right now, definitely take a look at that because you can do some really cool stuff within the B tree. And finally, last but not least, is the N-ary tree, where N is just a mathematical number that represents any number other than 0 or any negative number, of course, because negative space doesn't actually really work. And 0, having a 0-ary tree, the arity on that just, I don't know, arity 0 doesn't work. Sorry, no dice. Okay. But we'll take a look at those another time. So that's where we're going to go. Now, back to the self-balancing trees. The self-balancing binary trees are optimized trees. These are trees that actually make your data operate in a better fashion. It makes it a lot more efficient to actually work with this tree because of the fact that even though it takes some time to insert and remove data, the use of the tree, like, oh, I need to find something, search something, verify values, becomes much more efficient because the tree itself optimizes as you get the values built in. They get as wide and as flat as possible, so it makes it you have to do less calls and comparisons to find the information when you need it. Now, with a red-black tree, what it does is it uses an extra bit, just one little tiny bit on offset of information to determine whether the color of the tree node is going to be red or black. Hence, that's why it's using that bit of information. Now, it's a self-balancing rules that where all leaves are black, aka the ones at the bottom. Again, remember because the trees are lies outside. And if a node is red, both its child nodes will be black. So that means we have an approach with that all the child nodes of a red one have to be black. And then any path from a node to its descendant have the same number of black nodes. So no matter what right, left path I use to get down to that, I'm going to have the same number of black nodes no matter what path I take to get to this. Now you can take a look at this and do some examples of that. Again, take a look at, say, visualgo.net to see how that's going to work. You can see some really cool stuff. Maybe do another lecture on that as well. Now, we use also the idea of using rotations of the node structure so we can we use rotations of the values in the nodes so we can have the change color as needed because, again, it has to follow the rules of red and black structure. And so for that to happen, we use rotations to make those rules happen. And that's where we make the change to the tree to make it so it's self-balanced and has the appropriate relationship. The next one we have is the AVL tree. And we're going to take a lot more detailed look at this in class, but it's named for Adelson Velsky-Landis, the Russian computer scientist who actually invented this tree, and they made the data structure so we can actually really do some cool stuff. And it's a way of actually creating a tree that when you insert or remove the that as the insertion goes in, it puts the value in the appropriate spot, and then after the value is inserted or removed, whichever the case happens to be, it then examines the associated tree that is a result in subtree, that is a result from that. And if that subtree is then out of balance, it causes rotations to rebalance that subtree, which then bubbles up to the entire tree and causes a balanced tree overall every time you make an add or removal from the tree. And these are based on rotations of the tree. We're either going to do a left rotation around the root, a right rotation around the root, or a left-right rotation, or a right-left rotation. So you can actually take those rotations of the tree so it makes the tree balance itself. And it may cause an out-of-balance sequence, but then the second rotation of that makes it become more in balance. Really cool stuff. We'll talk about that more in class and have another lecture for it as well. But keep moving on. We also have, last but not least, as I said, the N-ary tree. And this is where, again, a binary tree is an example of this with two. A one-ary tree, an N-ary tree of one, that's not a tree, that's a list. Sorry, no dice. But an N-ary tree is any number 2 or greater where we're going to have multiple children and we're going to handle that. But because of the fact we don't know how many children we'll be handling that, we can't simply just make a whole bunch of pointers. I mean, I could, but we won't. So we take a look at the UML diagram over here on the left, and we can see that we have an N-ary tree node of type, has a root pointer, of course. We have to know who the root is. That's important. We then have a children data member. A children is a list of the N-ary tree node type pointers. Okay, we have a whole bunch of pointers linked in a list because that way we can go through and add them, and they can be sorted and structured and hold on to like that. And then we also have a size, aka how many number of nodes that we can possibly have in our children. So that's our max count that we're going to be working with. Our constructor, again, is going to take an int for that. No matter what we're going to do, we'll have an automatic value of how many number of pointers we're going to have within that, as well as a type int parameter, so we can actually build that one, and we have put the value in, and again, knowing how big it can be. We have our get and set root accessor methods, weird, kind of basic. But then we have, instead of our regular hashtag basic methods, we have an add child, which takes a single one and puts it inside the children. And then we have the get child, which will retrieve a single child, passing an int of the index of that value. And finally, we have the get children, which is going to be all of the kids, because sometimes we need to get all of them, I know. Now, when we're using an N-ary tree, we're going to be building our tree, the abstract base class. And when we just looked at earlier, we're going to build an abstract base class of that. We're going to extend it, make an N-ary tree, but have all those same basic methods. And when we're doing the traversals or the insertion, the removals, or any of the operations that exist on all trees, instead of having it adapted for a binary tree, we'll customize the code to match it so it'll work with this new tree right here. Now, again, when we're talking about the traversals, we'll have to make some changes to this, so we'll have to iterate through all the items in that list or vector. But again, vectors and lists, hey, those are easy. Those are linear data structures. We already have iterators that can go straight through them, or there's the easy magic process of a for loop. We're good to go. And so by using this structure, we can have an arbitrarily wide tree where we can store data in a customer relationship. So we can have, oh, it's between this range and this range, between this range and this range, this range. And we can build those trees out and have it be as wide as we need the data to be for having a very compact set of data. Now, again, this is some of the basics information about trees. There are more information about trees than I could possibly ever share. But again, just like we saw at the very beginning, there are many different types of trees. Have some fun with yourself and keep on learning. Thanks, and have a great day.